All right, we've done this logistic equation using separation of variables, which leads to a partial fraction decomposition. We're going to take our other approach today, which is a Bernoulli transformation. So if we distribute, we get this, which we rearrange to be y prime minus 1600 ky equals minus ky squared, which is the form we use for our Bernoulli transformations. Now remember, for the Bernoulli transformations, we're looking at the power of y here. In this case, it's a positive power, and our transformation is u equals y to the 1 minus that power. So in this case, it's u equals y to the minus 1, or u equals 1 over y. That means y equals 1 over u, and y prime equals minus 1 over u squared times u prime. Remember, the u prime comes from the chain rule, and when we do this Bernoulli transformation, we always have that piece. So we start replacing things in our differential equation. We replace y prime with y prime. We replace y with what y is, right? And y here with what y is. We can replace everything and get minus 1 over u squared u prime minus 1600 times k, and y is 1 over u, equals negative k times 1 over u squared, because y squared is 1 over u squared. So that looks pretty good. We've made our substitution. Everything is in terms of our new variable u now. And so now we're going to multiply through by a negative u squared, so that we get u prime plus 1600 ku equals k. And everything else canceled out. So that's nice. We've done our transformation. It worked out. We end up with a linear differential equation, and that's the deal, right? That's the Bernoulli transformation promise, is that that thing that you start with is going to end up as a linear differential equation in the end if we do it correctly. So we've done it correctly. We have our linear differential equation, and we're going to solve it with integrating factors. So I'll do a mu, not to be confused with u, is e to the integral of 1600 k dt. So our integrating factor is e to the 1600 kt. That's going to be our integrating factor. We multiply everything through by the integrating factor, and we know that that leads us to a u e to the 1600 kt quantity prime equals e, let's put the k, e to the 1600 kt here. I integrate both sides, and I have u e to the 1600 kt equals 1 over 1600 k times k e to the 1600 kt plus c. Get a little cancellation in the k's there, which is always welcome. We multiply through by e to the minus 1600 kt to solve for u. So u equals 1 over 1600, exponentials cancel, plus c e to the minus 1600 kt. Now that's our solution for u. And what we want to do now is remember what u is. U is 1 over y. So that is our 1 over y. To be able to invert that and get y, it might be nice if we have these terms on the right combined with a common denominator. So let's say that's 1 plus c e to the minus 1600 kt divided by 1600. 1600 c. Let me fix that. I forgot the common denominator part on the right. 1600 c e to the minus 1600 kt kt, that's 1 over y. So we have y equals 1600 over 1 plus 1600 times c e to the minus 1600 kt. And that is our solution via the Bernoulli transformation. We got, at this point we can put in our initial condition. We can solve there for the initial condition, see what we get. In fact, why don't we just do that? Y of 0 equals 2. So that's 1600 divided by 1 plus 1600c. So we have 2 plus 3200 c equals 1600. So c equals 1598 divided by 3200, which reduces to something. At any rate, that will go in here, and that'll be our solution. Now, this will be equivalent to the solution we found with partial fraction decomposition, separation of variables in the previous class. It looks a little different because we didn't absorb constants in the same way, but in the end, that will be it will be equivalent when we find what k is. It's all going to even out in the end and give us the same thing. So there it is, the solution with the Bernoulli transformation.